This is a screencast that has to do with example problems for chapters 6.1, section 6.1 and 6.2. So here is like one of the example problems on page 220. So as we go through this, you can flip to page 220. There we go. Page 220. This one right here is the first example problem. I'd like to take you through it. They show you like a way to do it. I'm going to show you basically the same thing, but the way I would do it. If you have questions, obviously, about where I'm getting the numbers from, take a look at page 220. And then, of course, ask me in class if you have any issues. The yellow light given off a sodium vapor lamp used for public lighting is a wavelength of 589 nanometers. So let's talk first of all about what nanometers are. We know that meters are right here. Meters, liters, and grams are at the ones place. If I go 3 places to the right, that is milli. If I go 3 more places to the right, as in like milli is 1,000ths, that's 10 to the negative 3. Micro is times 10 to the negative 6. By the way, these are all times 10 to the negative 3 meters, times 10 to the negative 6 meters, which puts nano out here at times 10 to the negative 9th meters, which is where I'm getting this information from. So when I first do any of these problems like this, what I tend to do is change wavelength from 589 nanometers to 589 times 10 to the negative 9th meters, okay, by simply using this conversion part. So anytime I have nanometers and I want meters, and I do want meters for this because I'm looking for the frequency, and to go between the frequency and the wavelength, I'm going to have to use the speed of light. The speed of light is listed for you in meters per second, so I'm going to have to change the wavelength from nanometers to meters. So let's continue on. Once I have my wavelength times 10 to the negative 9th meters, and you can do that anytime you have this nanometers term, that unit. So here I start off with C equals, this is one of those equations. There, I said in class, and I apologize that there wasn't much math in the second trimester of Honors Chem. There is some, and we're going to see a lot of it right now, but it's not nearly as much as it was in the first trimester. So this is one of those things where we actually do have math here. So this is wavelength times frequency, and here I have for, let me just back up here and plug everything in except for frequency. So 3.00 times 10 to the 8th meters per second. You may want to get to know that. That's the speed of light. That is a constant. That is a constant speed that does not change, at least as far as we know. And then we have wavelengths. The wavelength of 589 times 10 to the negative 9th meters, and all of that times frequency. So if I'm going to solve for frequency here, I'm going to divide both sides by the 589 times 10 to the negative 9th meters. Like this, and frequency then equals, as I find out, it's 5.09 times 10 to the 14th. So please make sure that you know how to multiply and divide with scientific notation on a calculator. That's very important. And this would be 1 over seconds then, because the meters cancel and I'm left with a value that's 1 over seconds. So this is the frequency, and you can also use, instead of 1 over seconds, you can also use hertz, Hz, because it means the same thing. It means that number of waves per second. Now it's an incredibly large number of waves per second, but that's what it is. So that's number 1. Let's take a look at number 2. This is going to be a very similar process. I'm not going to go into quite the detail we had before. So the laser used in eye surgery to fuse detached retinas, so that's a lovely thought, produces radiation with a wavelength of 640.0 nanometers. Calculate the frequency of this ray. Okay, so the first thing I do is I change this from nanometers to 640.0 times 10 to the negative 9th, and this will be meters. I'm going to do the same thing. Frequency equals speed of light over wavelength. I just did that in the last problem. All I did was algebraically change. If I'm doing this like that, I divide both sides by wavelength, which is how I got those canceling, and that's what this is right here. So 3.00 times 10 to the 8th meters per second, all that divided by, and this is going to be 64.0 times 10 to the negative 9th meters. Okay, so that'll equal, let's take a quick look what that will equal, and it looks like it is 4.688 times 10 to the 14th. Times 10 to the 14th, and that's 1 over seconds. Or sometimes you will even see seconds to the negative 1, and that means exactly the same thing. Okay, that's number 2. This is it for this screencast, and then tune in for numbers 3 and 4.